Good afternoon, everyone. My name is Yu Zhang, and I come from Tianjin University. I'm delighted to have this opportunity to share something with you. Today, I will focus on emerging carbon capture from methane carbon dioxide binary system using supersonic flow. My presentation will cover the following 5 parts, that is, research background, model building and validation, pure carbon dioxide condensation system, methane carbon dioxide condensation system, and final conclusion. Let's start with the research background. Climate change is a global issue that requires action. Climate science has produced mounting evidence that human-caused greenhouse gas emissions must decline if we want to limit global warming below 1.5 degrees Celsius. The Paris Agreement responded to this challenge by legally binding signatory nations to achieve a climate-neutral world by mid-century. The European Commission has also agreed on European Green Deal, seeking to foster a future with a decarbonized economy and net zero emissions by 2050. The European Commission released the proposal REPowerEU, Joint European Action for More Affordable, Secure and Sustainable Energy. The 25 net zero scenario developed by the International Energy Agency contends that no new oil and gas fields should be approved after 2021. In addition, at least 70% of the world's energy supply should come from wind and solar energy by 2050. This means the energy structure needs to be adjusted for a low-carbon future. Carbon capture and storage is one of the most promising technologies to tackle climate challenges. The separation of carbon dioxide is a critical step toward achieving the economic and technical objectives of carbon capture and storage. The present study proposed a novel carbon dioxide capture concept using energy conversion in transonic flows, which is not only a clean process of carbon dioxide processing, but also a way to maximum utilize the thermal energy. The working principle of supersonic nozzle, the core component, is that the contraction of the cross-section causes the expansion of gas, which reduces the temperature and increases the gas velocity. The generation of low-temperature environment leads to the condensation of carbon dioxide gas into nanodroplets. By integrating the principle of cyclone separations, carbon dioxide droplets will be removed to achieve carbon capture. The condensation phenomenon in supersonic flow has been numerically studied by many researchers, but there are still some problems. First, most of the subjects are water vapor. The condensation properties of carbon dioxide have not been explored, and most of the physical property equation in their models is ideal gas state equation. The ideal gas model cannot correctly reflect the phase change of carbon dioxide in high-pressure environments. Therefore, we have modeled the condensation of carbon dioxide in a supersonic nozzle based on a real gas model. Next, please allow me to introduce this new condensation model. In this model, the carrier gas is methane, whose mass, momentum, and energy conservation equations are listed in the upper left. The liquid phase is carbon dioxide, whose governing equation is listed in the upper right. Phase change between gas and liquid is manifested as condensation and evaporation, and is reflected in the source-term exchange in the governing equation. Condensation is divided into homogeneous nucleation and growth and heterogeneous growth. In the lower right corner is a formula for nucleation and growth. Here the equation of state changed from the ideal gas to the real gas law. Experimental validation was then carried out. The experimental data of the theory were exploited, so the same supersonic nozzle used by the theory was used for our simulation. The comparison between the experimental results and the simulation results is as follows. As shown in the figure, the blue dots are experimental data, the red line is real gas simulation data, and the green line is ideal gas simulation data. It is obvious that the real gas model corresponds better to the experimental results. The RMSE error calculation can also prove that the difference between the real gas model and the experimental results is smaller, and its RMSE is only 0.0147. And for the prediction of condensation location, the real gas model also shows greater advantages. Therefore, the established model can guarantee the accuracy of the calculation results. Subsequently, the carbon dioxide condensation characteristics in a pure carbon dioxide system were studied by using the established model. At an inlet pressure of 60 bar, the saturation temperature is about 295 Kelvin. Set the inlet temperature to 315 Kelvin, at which point the inlet gas state is superheated. The superheated vapor enters the nozzle and expands, gradually reducing the temperature and pressure. When the gas continues to expand into supersaturated vapor, the nucleation rate rises rapidly from zero in a short period of time. Condensation occurs when the nucleation rate is at its highest, corresponding to the Wilson point. The growth of the condensation nuclei restores the vapor to a state of equilibrium. This process is the condensation process of carbon dioxide in a supersonic nozzle. And this process can also be changed by adjusting the inlet pressure or temperature. Keep the inlet superheat constant. Decrease the pressure. Wilson point will move backward. Keep the inlet pressure constant. Increase the superheat. Wilson point will move backward too. Meanwhile, keep the inlet superheat constant. Increase the pressure. Superheat at Wilson point will decrease. Keep the inlet pressure constant. Increase the superheat. Supercooling at the Wilson point will increase. Now that we know how carbon dioxide condenses, let's switch perspective and look at the binary system of methane and carbon dioxide. Keep the inlet pressure at 8 megapascal, the outlet pressure at 2 megapascal. The inlet mole fraction of carbon dioxide vapor at 25% and increase the temperature. We find that with the increase of temperature, the condensation onset position moves backward and the subcooling degree at Wilson point increased by 4.53 Kelvin. The radius of the condensed carbon dioxide nanodroplets decreased from 0.44 micrometer to 0.29 micrometer. The nucleation position moved backward by 43.8 millimeter. The outlier mole fraction also decreased, and the amount of condensation decreased from 19.47% to 7.84%. Keep the inlet pressure at 8 megapascal, the outlet pressure at 2 megapascal, the inlet temperature at 273 Kelvin, and increase the mole fraction of carbon dioxide. We found that with the increase of inlet carbon dioxide mole fraction, the condensation onset location moves forward, and the supercooling degree at Wilson point decreased by 12.09 Kelvin. The radius of the condensed droplet decreased by 0.07 micrometer. The nucleation position moved forward by 39.8 millimeter, and the outlet mole fraction increased with the amount of condensation increases from 13.22% to 17.53%. And we also found that the presence of foreign carbon dioxide droplets will lead to the radius of the condensed carbon dioxide nanodroplets increase. The Wilson point location move forward, and the amount of condensation increase. For the following two reasons. First, the heterogeneous droplets evaporate in a superheated gas, increase the carbon dioxide vapor content. Second, foreign droplets with large diameters are more likely to act as condensation cores and promote condensation. Finally, I have made a summary. This study proposed a condensation model based on the real gas equation of state, investigates the condensation law of carbon dioxide in supersonic flow, and explores the effect of inlet conditions on decarbonization. Results show that the decrease of inlet temperature, the increase of carbon dioxide mole fraction, or the presence of foreign carbon dioxide droplets will lead to the Wilson point location move forward, and the amount of condensation can increase to 19.47%, 17.53%, and 18.26% respectively. The model is promising to be extended to other condensation systems for carbon capture to look for effective decarbonization ways and contribute to climate issues. That's all for my presentation. Thank you for listening. And if there are any questions, I would like to give further explanations.